All right, folks, so we're continuing with this series of videos on the remainder theorem. All right, I'm trying to keep the videos kind of short. Instead of making one long video at 45 minutes, we make 3 at 15 minutes. I'm trying as much as possible to reduce the number of excuses people have to not watch the video. So while I'm not necessarily promising excitement from start to finish, I will try my best to not have it too long. All right, and in the odd cases where I go a little long, I'm giving you the option to pause, stop, and come back again. So bottom line, no excuses. We proceed. So, let us start with one of my favorite quadratics that I love to work with anytime I have to demonstrate quadratics. All right? Let us consider the dividend. And what's the dividend now? The dividend is x squared minus 3x plus 2 as a dividend, and we're dividing that by x minus 1. All right? In fact, yeah, let me leave that just so. So in other words, we have this, and we have this. Watch it. We have, in green over here, we have x squared minus 3x plus 3 divided by x minus 1. Yeah? So, remember dividend divided by divisor. Now, if I tell you that the answer for this is x minus 2, if you were paying attention in some of the earlier videos, you remember that this is one of the, I would have used this as the first set of quadratics, right? To demonstrate quadratics and linear and all that, right? So your quotient is x minus 2. Your remainder, of course, is 0, because x minus 1 is, in fact, a factor of x squared minus 3x plus 2, which, again, I believe I would have demonstrated earlier on when we were dealing with long division. On the other hand, my good friend here, and I need to shift this around a little bit, because in this case, I will need some more space. On the other hand, my good friend here, x squared minus 3x plus 3 divided by x minus 1 is equal to what? Same x minus 2, but with a remainder of 1. Look at the thing start. Right? So we don't have any remainder here, so we leave it out. Over here, however, we do in fact have a remainder, and the remainder is 1. How do I know the remainder is 1? Because all I did is add 1 to this 2 here. I took 1 and added to this 2, and I get 3 here. So same quadratic, let's add 1 to it. So I know for sure that the remainder is actually 1. Now, let us discuss this with respect to the remainder theorem. And then we start over here. What this means here is that x squared minus 3x plus 3 is equal to x minus 2 dot x minus 1 comma plus 1. All right? Now, we could see by looking at x minus 1 that the root of the equation x minus 1 is 1. How do I know that? Very simple. The root of x minus 1, which is the root of the divisor x minus 1, is equal to 0, x is equal to 1. So in other words, if we substitute 1 right through this expression, we will see what happens. All right? So if we substitute 1 here, you will get 1 squared minus 3 by 1 plus 3 is equal to 1 minus 3 plus 3. Minus 3 plus 3 is 0, which would just be equal to 1. Look the same one there. Look it right there. Alright? And if you want to demonstrate it over here, we're going to do the same thing. Again, you're looking for the root of the divisor. X minus 1 is equal to 0. Therefore, x is equal to 1. So, just as we did over here, we finish it over here and we say that x squared minus 3x plus 2 is equal to x minus 1, comma, x minus 2. It has no remainder, so we leave that just as is. Now, x minus 1 will make this whole thing equal to 0, just as was the case here. This whole expression went to 0, and when we had the 1 here, we end up with the same 1 across here. So, similarly, over here, we know the remainder is 0. We put it here just for emphasis. And we substitute the same 1 over here, and we say the same 1 squared minus 3 by 1 plus 2. This time it will be 1 minus 3 plus 2, which will be minus 2 plus 2, which is, guess how much? 0, which is the same 0 here. So in other words, in both instances, let me put this in red on top here, just so that you don't lose sight of it. X minus 1 is equal to 0, so x is equal to 1. Alright? In both cases, your big D, and then we go back in general now. Alright? Remember that big D R, where R is the root, is equal to QR by small dr plus big R. Right? And big R, of course, means that d of r is equal to 0, small dr. So q r by dr is equal to 0. So therefore, we remember that big dr is equal to the remainder. This here is basically what we refer to as the remainder theorem. Alright? This guy here. That is the remainder theorem. So in both cases, dr was the remainder, because over here we got that d1 with divisor 1 was equal to 1. We saw that here, d1, this is a divisor, we substitute 1 and we end up with the same one that we had over across here. Sorry about that. And over here we have that the same d1 is equal to 0 in this case. Alright? Where the remainder was 0 because x minus 1 is a factor of x squared minus 3x plus 2. So in general, once we know that, once we have the root of the divisor, we then substitute the root of the divisor into the dividend. And whatever we get from that is the remainder. So in other words, the remainder theorem, what that allows us to do is to not have to go through all the long division. Alright? We could just simply substitute the root of the divisor into the dividend. And whatever we get, that is the remainder. So for example, let us assume, for the sake of argument, and I'm going to illustrate that by rubbing off the board now. Let us assume, for the sake of argument, that we didn't know that x minus 1 was a factor of x squared minus 3x plus 2. We didn't have any idea of the relationship between those two functions. Alright? So suppose you get a question like, and this is the template generally This is a very simple version of a general question that you will get at various levels in the advanced. What if they had said, find the remainder, right? Find the remainder when x squared minus 3x plus 3 is divided by x minus 1. Yeah? Aha. Right? We could do that too. Now, this is your dividend. This is your divisor. So, the first thing we do is to find the root of the divisor. Alright? So we say step 1, if we want to say, put it in steps. Right? Find the root of the divisor. Right? So we put the equation down. X minus 1 is equal to 0. So therefore x is equal to 1. Step 2. Substitute the root into the dividend. Right? Remember, the dividend is the thing that is divided. Alright? So in this case, the root was x equal 1, so we substitute 1 into our good friend here. So in this case, we say that when we substitute, we get that 1 squared minus 3 by 1 plus 3 is equal to 1 squared is still 1, minus 3 plus 3, minus 3 plus 3 is 0, and I get 1 as the answer. So, without any previous knowledge of the relationship between x squared minus 3x plus 3 and x minus 1, we have now a straightforward mechanism to find the remainder when x squared minus 3x plus 3 is divided by x minus 1. That's remainder theorem. That is remainder theorem in action. Of course, the actual applications of the theorem itself would be a little more complex. So for example, when we factorize in and all this kind of thing, right? But at the very core and at the very heart, this is what the remainder theorem is. Now, I'll leave that up and we're going to flip the script. Now, if we say now instead of x squared minus 3x plus 3, we say find the remainder when x squared minus 3x plus 2 is divided by x minus 1. So in this case, same x minus 1, but we change the dividend to x squared minus 3x plus 2. So again, step 1, find the root of the divisor. X minus 1 is equal to 0, x is equal to 1. Substitute the root into the dividend. Boom. In this case, we have a slightly different scenario because we have a different dividend to start with. Alright? So, we say in here that x, that will be 1 squared minus 3 by 1 plus 2, which would be 1 minus 3 plus 2, which would be minus 2 plus 2, which will be equal to 0. And that's it. So, we find the remainder and we realize that the remainder is 0. What does it mean when the remainder is 0? Just as with irregular simple numbers, 9 by 4 is 36. 36 divided by 9 is 4. Remainder is 0. If the remainder is 0 when we're dealing with regular polynomials, what it means is that the divisor is a factor of the dividend. And that is what we refer to as the factor theorem. Now, sometimes they just generally refer to it as the remainder and factor theorem, which makes sense to me because the factor situation is actually a very specific instance of the general remainder theorem, right? The factor theorem is just when the remainder is 0. But once the remainder is not 0, it does the remainder theorem. So in other words, if we have to employ the language of sets, we could say that the factor theorem is a subset of the remainder theorem. And the specific condition that instigates the use of the factor theorem is when the remainder is equal to 0. That is what defines something as being a factor of something else. All right? So that's basically it. I would have demonstrated using simple examples. The next video, what I will do is demonstrate using some of the same examples that we would have utilized in the long division videos. Right? Remember, we did some examples with the long division. I will demonstrate the remainder and the factor theorem using those same examples, and that basically would close off our discussion of the remainder and factor theorem and set us on the course now to start doing questions. Of course, we start off with doing some easy questions just to get the rhythm of it, and then we shift into the past paper questions where, of course, there will be a slightly higher level of difficulty, which would now be where we had to think a little bit. We might have to fall back on some other aspects of mathematics. Yeah, that is add maths. Yeah? So keep good, stay in the game, and we're looking forward to the next video following up from this one.